Okay, in this session here we will start our PowerPoint session by looking at Chapter 1 of our book dealing with matter measurement and problem solving. These PowerPoints were put together by Roy Kennedy of another community college, but it's being used with our book, and so we will proceed. First thing we'll look at is the composition of matter, where we'll look at atoms and molecules, and then look at the scientific method. First thing we'll look at is how structure determines properties of matter. The properties of matter are determined by the atoms and molecules that compose it. Two examples here. One's carbon monoxide. If you look at carbon monoxide, it has one carbon atom represented by this one and an oxygen atom represented by this one. And if you look at the properties of them, carbon monoxide, it's colorless, odorless gas, burns with a blue flame, and it can even bind to hemoglobin. If you look over here with carbon dioxide, its structure is we have one carbon atom connected to two oxygen atoms. And look what happens to the properties when we add an extra oxygen atom. It still remains colorless and odorless as a gas, but it does not ignite, it's incombustible, and it does not bind to hemoglobin. When we look at atoms and molecules, atoms are what we call submicroscopic particles. That is, we can't see them. And they are the building blocks of matter. In fact, they are the building blocks of molecules. Our molecules are two or more atoms attached together in a specific arrangement. Their attachments are called bonds, and these attachments can come in different strengths and in different lengths. So we define chemistry as the science that seeks to understand the behavior of matter by studying the behavior of atoms and molecules. We'll now begin our look at the scientific approach to knowledge. If you watch my two videos on science, we'll get into this in more depth. Let's go over this, what's presented here. So what we're trying to look at is the ideal behavior of knowledge, and scientists gain it through empirical knowledge, which is gained by observation and experiment. So the word empirical basically means observation, and we get those observations by doing different experiments. So when we look at observations, we have two kinds. One's a qualitative. Okay, here's an example of qualitative. The soda pop is a liquid with a brown color and sweet taste. So that's qualitative. Quantitative deals with numbers. Okay, so qualitative deals with description. Quantitative deals with numbers. So we're looking at, for example, 240 milliliters of pop that contains 27 grams of sugar. One of the first things we do in the scientific method is build a hypothesis. And a hypothesis is a tentative interpretation or explanation for an observation. So, for example, we might say the sweet taste of soda pop is due to the presence of sugar. A good hypothesis is one that can be tested to prove wrong. Is it falsifiable? In fact, one particular test might invalidate your hypothesis, and then you have to start with a new one. Ideas in science are tested with experiments. So an experiment is a controlled procedure to test whether an idea is valid or not. Experiment generates observations that will either validate or invalidate the idea. A scientific law is a statement that summarizes all past observations. Key here, it's able to predict future observations. An example of a law is the conservation of mass, which says that in a chemical reaction, matter is neither created or destroyed, it's conserved. A scientific law allows you to predict future observations so that you can test the law with further experiments. So we go from specific to general understanding. Hypothesis is a potential explanation for a single or a small number of observations, whenever that be for. So the scientific theory is a general explanation of why things behave in nature the way they do. And here's a little diagram. Won't get into it too much here, but we basically come over here and start with observations. We can form a hypothesis about it. We can then get a theory and then confirm the theory by a number of experiments. We can produce a law that gets confirmed again and again by doing experiments. See, the key here is repeatability. Once I find one experiment that does not conform to this law, then the law is invalid and you have to adjust the law somehow. So here's the relationships between pieces of the scientific method. We'll just move on from here. Okay, classification of matter. We're going to look at the states of matter, physical and chemical properties, and changes of matter. We're going to look at the classification of matter. Remember, matter is anything that occupies space and has mass. So we can classify matter based on its state and its composition. When we look at its state, we're referring to it being a solid, a liquid, or a gas state, and its basic components, which is where we get the word composition from. So if we look down here, we have the different states. Here is a solid state. Look at how the particles are very close together, stacked on top of each other. When we go to the liquid state, note the particles get a little bit separated. Then we go to the gas state. Look at the particles now. They are very separated from each other. So we can classify matter by its physical state, solid, liquid, and gas. And here's some explanations. The shape, solid is rigid. The liquid assumes the container's shape as well as the gas. The volume is maintained by a solid and liquid, but the volume is assumed by the container for the gas. Is something compressible? Well, that means can I squeeze it, like squeezing it together with a piston. A solid is incompressible as well as a liquid, but a gas, we can compress it. Same thing with flow. A solid does not flow, does it? But a liquid and a gas can flow. So here are a picture of solids in a little bit more detail. Okay, solids have the particles that are packed together. And here's a blow-up of the solid. So you can see that solids are incompressible because there's really no space between the particles to squeeze them. You can have a couple of different kinds of solids. One's a crystalline solid, where we have what's called long-range order. So if you look at a picture of a diamond in a microscopic view, you can see the atoms have a particular order arrangement to them. Versus what's called an amorphous solid. This is one where we don't have long-range patterns. So if you look here, there's no particular pattern to these atoms being stacked together. so we call it amorphous, which means without shape. Liquids, a little bit different. So here the atoms are a little bit more separated. In gases, they are much more separated, and they are able to fly around like crazy, bump into each other in the container. So we say in a gas state that there is a lot of empty space between the particles. So here's a picture of what we were talking about, meaning compression. We have a piston with the gases we're able to push down because of the extra volume between the particles of a gas. Now let's look at composition. So we can classify matter in its composition. One, is it a pure substance, meaning that's the only substance there. As a pure substance, it can be either an element or a compound. If it's an element, it means it's the pure atoms by itself, for example, helium. Versus if it's a compound, we have different atoms attached to one another, making up that substance, such as water. Water is composed of hydrogen and oxygen bonded together. The other way to classify is a mixture. It can have hetero or homogeneous. Heterogeneous, we see two different phases down here, say between sand and water. But a homogeneous, there's no two different phases. Everything kind of agglomerates together, such as tea and sugar in water. So here's further definitions for the pure substance versus a mixture. Here's the breakdown of matter once again between a pure substance and a mixture. You can read the properties here. Elements, what are they? These are things that cannot be broken down. They're the basic building blocks of matter. Usually they are composed of single atoms, but we'll see later that some elements compose of the same atom bonded two or more times to one another. And compounds are two different atoms that are bonded together. Pure substance, again, we've gone over those, can have an element or a compound, such as a glass of water. A homogeneous mixture, we have uniform composition, versus a heterogeneous mixture, we do not have uniform composition. Okay, let's look at changes in matter. We can have what's called a physical or chemical change. A physical change is one that does not change the composition, versus a chemical change, it does change the composition, meaning it rearranges, the atoms rearrange into new molecules, but all the original atoms are still present. So here's an example of a physical change where we are boiling water. If you look at water in the liquid state versus in the gas state, the only difference is that they become more separated, don't they? But you still have water molecules in both states. The composition doesn't change for a physical change. Versus in a chemical change, if you look at iron, you have in this composition, but when it rusts, oxygen atoms come in and we get a new structure. We get a new type of substance, which is what's involved in a chemical change. And so we can call what are called physical and chemical properties. Physical properties are properties that change, but we have no change in the composition. Chemical properties, we do have a change in composition. So an example of a physical property is simply dissolving, say, sugar in water. When you dissolve it, you still have sugar molecules and you still have water molecules. Same thing with boiling, melting, and these other things. Chemical changes would be things like rusting, burning, dyes fading, and so on. Here's an example of a reaction. If you look on this side, it's different than on the right-hand side. And that's what a chemical change is. You're getting new molecules forming as a result of these things reacting on the left-hand side. Now let's move into looking at what's called the standard units of measure. The standard things that we look at are length, mass, time, and temperature. And the units are meters, kilograms, second, and degrees Kelvin. So the length in meters, or even go to centimeters, and sometimes we use inches. You can see the conversion to go from inches to centimeters. So we need to know lengths of very long distances and very short distances. For mass, we generally use the gram or kilogram. You can see down here the conversion between, say, a pound and a gram, and these other things. We generally use a scale of some type to measure the mass. Time is measured in seconds. And temperature, this is the measure of kinetic energy caused by motion of particles. We'll get into that definition later, but basically the higher the temperature, the larger the average kinetic energy. So heat flows from matter that has high thermal energy into matter that has low thermal energy. So heat flows from hot to cold. And these are our units for Celsius, Fahrenheit, Kelvin. These are equations you'll need to know of how to convert between one unit and another. Here are the temperature scales, Fahrenheit, Celsius, and Kelvin. Kelvin is sometimes called the absolute temperature scale because it has the lowest temperature, which is absolute zero, at zero, which corresponds to these other temperature scales. Fahrenheit versus Celsius. You can see this conversion, so you need to have this memorized. And here is the Kelvin and Celsius conversion. And here are some problems that you can look at where they're giving you 40 degrees Celsius and they want you to convert it to Kelvin and Fahrenheit. So you can look at how they did that down here below. Here's some more practice converting 0 degrees Fahrenheit into Kelvin. Again, you can read that on your own. One of the things we're going to start getting into are what are called the prefix multipliers. Okay, covered this in the video segment. And we'll go over this briefly here. So here are the prefix multipliers, everything from the mega all the way down to the pico and everything in between. And here's the power of tens. Remember, these powers always go with the base unit when doing the conversions. Volume can be measured in cubic meters or centimeters, or it can be measured in milliliters. Remember that 1 milliliter is 1 cubic centimeter. Okay, here's some common length units and conversion. Key one here is 1 inch is 2.54 centimeters. Mass, 1 pound, 453 grams, and the volume conversions. So you don't need to memorize all these, they're just showing you the different ones. Okay, in here, which of the following is best for the diameter of a quarter? Probably the centimeter. Now on to density. Before getting to density, we look at what are called extensive versus intensive properties. Extensive are properties that depend on the quantity or the amount of matter, such as the mass. Intensive are independent of the amount of matter. An example will be the density. So mass and volume are extensive because they depend on how much you have. The density is intensive. Here's the definition of density that you need to memorize. Mass over volume. You can see the various units for density. Density of solids tend to be much greater than liquids and gases. Big exception is ice. It's less dense than liquid water because you see it floating on water, don't you? Here's some examples of densities of different compounds. See, lead has a very high density. Even mercury, even higher. Look at that. Water, density of 1, easy to memorize. And then everything in between. Generally, heating an object causes it to expand, so the density can change with temperature. And here's an example of calculating the density, just plugging the mass and volume in. Another example of the density problem. Let you go through that on your own. Now on to measurements in significant figures. A measurement is a basic observation which will have a number and a unit. So if I'm measuring this amount of liquid, it's coming out to 4.56 just about, isn't it? Okay, so the unit tells you what standard you are comparing your object to. And we generally estimate the last digit, which makes that last digit the last significant figure. Here's some examples of measurements. Measuring the mass of this peanut. You can see this one over here. It gives a little bit extra here, doesn't it? 1.27, so a little bit more accurate over there. So that brings us to significant figures. We look at a measurement and we see how many numbers there are. 12.3. This one has an extra significant figure of 0. So we have 4 in this one, 12.30. Here's the rules for zeros. All non-zero digits are significant. Interior zeros are significant, but leading zeros are not. So these 3 are not, but these 2 are. So we'd have a total of 1, 2, 3, 4 significant figures. Here's some other examples that you can look at. At the end of a number, it could or could not be. So the person has to tell you. So if I tell you this only has 2, then you report it in scientific notation as 2. If I tell you it has 3, then I report it in scientific notation as 3. Then you have what are called exact numbers. These are counting numbers. So if I have 12 eggs, I have 12 eggs, and so on. Here are some examples you can go through to see if you can figure out the number of significant figures. Some more examples. Now when we multiply and divide, we have certain rules. So if we were to multiply these numbers, we choose the number that has the less sig figs in it, 2. So my answer could only have 2. Same thing down here. This one has 3. So my answer I round off to 3. Note that the 5 became a 6 because of this outer 9. Adding and subtracting, I look at the lowest one with digits to the right of the decimal. So this one only has 2, so my answer will only have 2 to the right, 5.41. This number up here only has 1 to the right, so my answer will only have 1, and that 7 bumps up the 6. Okay, so here's our rounding rules that we've gone over. You can read over those. Some more rounding. And some more. Okay, what happens if you're multiplying, doing all these things in tandem with each other? Well, do what's in parentheses first, get that number, and then do the multiplication. And here's some examples. Precision and accuracy. Accuracy tells us how close a measurement comes to the actual value. Precision is how close a repeated number of measurements are to each other. So we're looking for a clustering effect in precision. Okay, we'll look at errors. We can read over that. Move on from there. And solving chemical problems using dimensional analysis. Let's take a look. Note when I multiply 2 units, it becomes squared. If I add them, it still stays the same. If I divide the 2 units, they cancel and you get 1. And what we're going to do is what's called dimensional analysis. So dimensional analysis, what I'm doing is I'm trying to convert one unit to another unit. So I start with a given unit. I use my conversion factor, putting the given unit on the bottom so those cancel. So I end up with my desired unit. Then you can even have more than one step. Okay, so here, converting inches to centimeters gives you a conceptual plan. Here will be my conversion factor that I use. And here's a problem-solving strategy that you can read over. Suppose we wanted to convert this many yards to centimeters. We would go from yards to meters, then to centimeters. So here's our conversion. And then here, using our prefix multiplier. And then we end up rounding to 3 significant figures because this one only had 3. And some more practice. You can read over that. Sometimes you want to convert cubic inches to cubic centimeters. I need to cube my whole conversion factor if I'm doing that. So here is an example going from liters to, say, cubic inches. So I start with liters, convert to milliliters, convert to cubic centimeters, 1 to 1, remember. And then down here, 2.54 centimeters per inch, but now I cube both parts so that my cubic centimeters will cancel with that one. And we get our answer. Okay, another example. Once you read over that. The density is a conversion factor. If we know the density of lead is 11.3, we can convert cubic centimeters of lead, its volume, to its mass by simply multiplying by its density. Or if you're starting with liters and wanting to go to kilograms, you can go through this strategy. So down here, liters to milliliters, milliliters to grams using the density, and then the prefix multiplier to give us kilograms. So that's the end of these slides, and we will stop here for now.